Well, then let's get started. And yeah, thanks for the presentation from Chen Yuan about the Llama model family. So my name is Zhe. I'm a research scientist from Apple. So today I'm going to talk about multimodal LLM pre-training in this session. So I think that both Li Zhen and Chen Yuan just mentioned multimodal LM has been a very hot research topic, and then we can see rapid progress both from the closed source models such as OpenAI GPT-4V and also many other models such as Gemini and also Grok 1.5V and others. But then on the other side, such as the Llama model family, right, we see tremendous progress on the open source model as well. Go beyond the Llama Next, we also see Q1VL, Intern VL, so X Composer, Vela, Emu2, etc. So the essential idea, as as I would say, so Chen Yuan just mentioned, it's so I think visual instruction tuning has been a central topic in this community. Basically, we first have lightweight alignment stage followed by the SFT, and mostly the SFT data needs to be high quality. So either you need to do human annotation or otherwise just use your GPT-4 or GPT-4V to annotate the data. And I would say basically all the model, all the papers. So indeed there are tons of paper for this. So in this line, so I think all the papers basically follows roughly the same pattern. So using the Llama model, but then with some recent focus on even higher image resolution and also even stronger LM backbone. Indeed, the performance is very strong, right? So we can see, and then in many of the benchmark, the model, so performance so is already very close to the top tier so models such as GPT-4V. So the question that so here we're going to ask is then the problem is, do we still need a large scale multimodal pre-training if so lightweight alignment is so all you need, right? So I think this is a very important question that so probably we don't have answer, but I think probably the answer is still yes, right? Because we still believe so large scale pre-training is still essential. So first, the pre-training is very crucial for the model to understand and digest the abundant multimodal so knowledge and the interactions in our visual world. And the second, so if we can do pre-training, this will go beyond the shallow alignment that is happening in the Llama model or in the so recent visual instruction tuning models. So pre-training indeed have the opportunity that we can learn deep multimodal fusion, especially when you have so web scale data that we can mine from the web. And then if you look at the pipeline in the Llama training, so we have the pre-trained LLM, we also have the pre-trained clip, then we align them together. So essentially in the end-to-end Llama training pipeline, right, we see the image text data and we also see text-only data. But then this data may not be sufficient to learn a really powerful multimodal model. On the other hand, there is another data type that is abundant. So basically, whenever you visit a web page, so the data is in this format, is the interleaved image text data. So basically, using interleaved image text data mimics LM pre-training. So it's your image and the text will just interleave in a very natural order. So this is actually very similar to the way how we do LM pre-training. And also this will provide us the opportunity to incorporate multimodal data from the start of your model training cycle. And even we can consider the possibility of using multimodal data to improve the LM itself. Well, also by doing the such kind of pre-training, typically one capability can be enabled, which is the multimodal in-context learning. So if you think about the multimodal in-context learning, the concept is actually very similar to instruction following. So in visual instruction following, you're given an input image, and then you also have an instruction. and then you will give the model will provide your response. But then in context learning, right? So basically, all your in context demonstration can be considered as your instruction, and actually it is multimodal instruction, right? But then if we simply do instruction tuning, this in context learning capability could be lost. So lastly, I think pre-training provides the flexibility to go beyond the Lava style architecture. So Lava is indeed popular in the last year, but then we also have model architecture go beyond the Lava, right? We may not. So I think generally the answer is open. We should not just focus on the architecture. That is, you have a clip image encoder, and then you have an LM, and then you hook up them together. But then indeed there are many other model families such as FUYU, right? And also such as CM3 or SEED, this kind of model that is so need your large scale pre-training essentially. Well, so I'm not sure this is convincing or not, but then at least I think we should keep keep this door open. So, but then before I'm talking about multimodal LLM pre-training in today's topic, I'm going to first revisit a little bit about what's the history of multimodal pre-training from my perspective. So I think roughly the journey started 5 years ago. If we just look at the paper or the literature, right? So back then I think it's BERT coming out, and then quickly in the multimodal community, we also have a BERT-like model. We have the pioneering work such as LexMert, BERT, and models such as United. So I think back then it's just the encoder only, very BERT style. And then the scale at that time was already considered as a large scale, but then usually it's just less than 10 million images. Well, it took almost 2 years for us to go through BERT style pre-training to the GPT style pre-training. And then in the middle, we can witness the appearance or the invent of clip model, right? And then I think the clip model, although using the contrastive pre-training, and the aim is different. Clip aims to train an image encoder, but then for multimodal LLM, it's more likely you want to train a generative model. But clip is indeed opens the door of really large scale pre-training. If you think about LexMert or United, this kind of model, scale is billions. But then if you think about clip, it opens the door to show using billions of image data and billions of multimodal data can just learn a really powerful encoder model. So I think so 2 years, then we move from LexMert to Frozen. So Frozen is from DeepMind, SimVLM is from Google, right? And the SimVLM is more like how you can just train a multimodal LM, so from scratch. All the parameters are just randomly initialized. As long as you feed your data, then the model will learn. But surely at that time there was some limitation, right? Because we don't have instruction tuning and instruction following. The concept has not been popular yet. So as we can see, Frozen model, the training objective is very simple, right? Compared with the BERT style training, typically you will have masked the image modeling, masked the language modeling, and also image text matching, and even image text contrastive learning. In Frozen, the training objective is just to predict your next token, and then so that's it. Okay, then it took another 2 years from Frozen to the current just well-known GPT-4. So I think in the middle, we can also see the Frozen has been evolved into Flamingo. We have all talked about it. So Trina has also talked about it. And then we also evolved from SimVLM into Coca, right? So how we can train such a image text foundation model. And then, so I think the last year is really witnessed the boom of visual instruction tuning. And then in this period, I think most of the work just focus on SFT or relatively small scale. And then I would say in the last 1 year, those works that focus on pre-training are so relatively so seldom. So some good example, so for example, the Vela, the Emu2, and our MM1 are some of the examples that still well, so I would say other model also do pre-training, for example, Q1VL, right, another model. But then most of the research paper would still just focus on the SFT stage. Since we have trying to motivate so pre-training for such a long time, then so maybe it's time for us to go into it. So so in this talk, I'm going to use MM1 as a case study to show how we can build a performant multimodal LLM with large scale pre-training. And then after using MM1 as the one example, we're also going to talk about other model family, such as Fuyu, CM3, so these kind of models. So we're using the MM1 as the case study. I will first just high level talk about what's the current popular architecture and also the recipe to build the MM1 and also how we can scaling it up. So first, the overview. Well, this happens again. Yeah. Seems not very reliable. Yeah, no, it's good. Yeah, so first the architecture review. So I think for this kind of model, in Flamingo, right, is using cross attention model. And then we also did some investigation in the cross attention model. But then I think for the more popular trends is just the decoder only style. You just have a LM decoder and then that's it. So then the good thing about using a decoder-only model, I would say, is to keep your flexibility of accepting any interleaved image text sequence. But then in Flamingo kind of model, due to the use of cross-attention, then when you deal with interleaved image text data, you need to take more care in order to deal with interleaved image text data. So given any interleaved image text data, we have an image and then we have text. Text will become token, and then token will become embedding, right? But then for the for the image part, then so typically so there will be something called so image encoder, and then typical in the form of VIT will translate the image into embeddings, and then you will, from the LM perspective, the input is just a set of embedding, but then this embedding can be image or can be text. And then the core part is the LM decoder, right? So so I think we so explore the both so dense model and also the mixture of experts variant. And from the dense model, we have the 3B, 7B, and the 30B model in the paper. And we also just directly use the pre-trained LM as backbone rather than using the instruction tuning version. So I think many of the so research paper using visual instruction tuning. So the typical choice will be an instruction tuned model or the post-trained model. But then in our case, since we are going to do pre-training, so I think using the base model could have a higher potential, well, in some way. So yeah, so I think this is the LM part, so which is so transformer by its nature. Then is the image encoder. Well, indeed, there are so many image encoder out there, right? But then I think the very classical one is just the plane vision transformer. And indeed, in our work, we're just using the plane vision transformer, trained using the clip objective. Surely you have other choices, and then you can even so using so image encoder so beyond the giant model size. But empirically, indeed, we also kind of observe even increase the image encoder to an even larger model size. Seems the effect on the final downstream performance is not that clear, which we will probably leave for future work. Then we have the connector. Basically, connect your image encoder and your LM, and then the embedding will send it into your LM. So there are many different choices for the connector, so which I will talk about later. But then the key idea is just to aggregate your image patch representation into a fixed number of feature vectors. And here we are using the C abstractor, which is some form of convolutional operator. So finally, the pooled representation will be connected with the text token embedding. So from the perspective of LM, it will just be embeddings. So indeed, we find just by the pre-training without touching the post-training part, the pre-trained model actually indeed shows very strong in-context learning capability. And I would consider in-context learning is also one kind of instruction following, as I just argued in so a few minutes ago. So well, the in-context learning capability is no surprise, but then indeed, due to our good recipe, we indeed find, so in our in-context learning example, the model can do counting, can follow the pattern of counting, as shown in the first example. You wanted to count the objects, how many dogs in this case, and also how many frisbee, and then the also follow the instruction, right? So it's output in the JSON format, basically. So in the second example, we also show such pre-trained model can actually have the visual plumbing capability in the base model so itself. So even without the instruction following or in the latest stage, the visual prompting capability is already there. So here, when I say visual prompting, so it means so when you draw a circle or draw a bounding box or just point one point, and then you let the model to follow. The model can know, so what do you mean? So here, we draw a circle on every, the OCR part of each image, right? And then the model can also output the text on the identified text region. So lastly, so in-context learning can also enable the model to do reasoning already. So if you show, so if you check the last row, so basically it's so you need some wisdom or kind of intelligence to do this task. Is you need to first identify how old is the girl or the boy for this birthday cake, right? And then you will do the add operation. So for example, in the last image, the first image is a 4-year-old so birthday cake. Second one is 1-year-old, and then 4 + 1 = 5. And then due to your pre-training, right, you basically say interleave the image text model. So interleave the image text data. So very naturally, you can reason across images. So this is the capability. So we can just inherent so from the pre-training. So know that the capability. So in the model that we show here, we didn't use interleave the data in your SFT stage. So the multi-image capability are just so it's inherited from your pre-training state. But then how to build such a model? So I think now we know the model, right? So this is the encoder, this is connector, this is your LM. So how we can train such a model? So for the ablation study here, we use due to ablation can be a lot, so we use smaller model. So the image encoder is a VITL, and then the connector is a C objector, and then we use 1B LM as the default setting. But in some cases, we also use the 3B LM. And then we also use a mix of caption the images, interleave the image text, and also text-only data as the pre-training data mixture. And then in some cases, interleave the image text data is important for you to recover your text-only performance. Due to interleave the image text is actually just very similar to your text-only data. For evaluation, we mostly focus on few shots. And even the more comprehensive instruction tuning evaluation at the later stage. So we will do 0, 4, and 8 shot average on a variety of captioning and VQA data sets, including the popular ones, including the text VQA and OK VQA, etc. So there are many moving parts in this story, in this model. So on the left figure, so we can see how you can accept your image, what's your resolution, what should be the connector, right? And then on the right side, how you want to balance all the data, why this data is important and that one is not important. So yeah, so the first thing that we do is the image encoder. So we consider two types of image encoder, all trained by ourselves. So the popular one is the clip model, right? But then you would consider why we should use clip. You could probably use also using other types of image encoder. Well, one popular one that has been studied in the literature, I think, is the DynaV2, right? There are paper studying using DynaV2 as the image encoder, but here we're studying another more just autoregressive trend, so image encoder, so which is also from Apple, so called AIM. So the AIM model is very simple. It's also an image divided into patches and then flattened into a sequence. And then your output is not a token, but then just the L1 loss on your, so regress to a pixel value. So this is how the AIM model is trained, and then they have the model size from 1B goes to to 7B. So here we want to study whether clip is the only choice you can have, or you can also use other types of data. So this is the table that we have. So I think we pre-train the image encoder, both AIM type and the clip type, and also different model sites using the DFN file B and also the VCAP 300 million data that we will mention later. But then basically, so DFN file B is so image text so data. So this data is also by Apple. So I think it's also there's a paper called the data filtering network, so which shows how we get the data. And then the highest native image resolution that we can afford is 378 pixel. So I think typically clip model are trained with 224, right? So if you go higher, it's a 336. Then we are kind of thinking, well, what's the highest resolution we can afford? So the one that we use is so we can go to 378 pixel. Then we will, in order to do this study, we will further perform multimodal LLM pre-training with the pre-trained image encoder through this study. So high-level results, one is, so I think the AIM pre-trained image encoder shows great potential. Well, this means, so maybe we don't need to use clip by the end if we can do large-scale pre-training. But then, so surely we will leave study, more careful study for future work. So another is image resolution. So I think you can choose, so the high-level results is, well, the higher resolution, the better. So the impact of the resolution goes beyond your size of your image encoder. Yeah, so has the highest impact followed by model size. Then it's the real connector, right? Indeed, there's also a lot of choices. In Lava, it's a linear layer. In Lava 1.5, it's MLP, right? And then, so I think in EMU2, it's just a simple average pooling. We also have other choices such as Q-former, perceiver, attention pooling. And also recently, I think in the Honeybee paper, so I think it's also a CVPR paper this year. They also have the so-called C abstractor and the D abstractor, so which do some so convolutional mapping. So I think in this study, we have studied all these type of so well connected. Well, the high-level message, if we do not so look into the figure in detail, is really we find. So I think this is also the message. I think it's Chunyuan also shared just now. So it seems the most important thing that matters is how many image token you can afford. The more, the better. And then how large the image resolution you can afford. The higher, the better, right? So which is very simple. The only difference is, so I think we are doing this so in the pre-training stage, and then so do this study. So later on, well, but then due to you are doing pre-training, so the image resolution you can afford can just be that small, right? So I think so later on we will also discuss how we can deal in the SFT, which can be lightweight, how you can further increase your image resolution for supervised fine-tuning. So we also have well, data is so very essential basically for pre-training. So here we consider in the high level 3 types of so data. One is capturing the images. This is basically your image and the text pair. And then another is more high quality and long form captions using some synthetic ways. We also have interleaved image text data and also text only data. And then this is roughly the model size that we have, and then the data sets so that we have. So for image text data, we have using 2 billion so web-mined image text data at scale. And also, so usually it's not that difficult for you to get large volumes of pre-training data, but the key is how you can do the filtering, right? So we should at least do some basic filtering, like so like a clip filtering, but surely you can do more. because the large and the noisy nature of such data. So due to all text can be very noisy, and even if you do the clip filtering. So although the example that I show here, they are good, right? But then the example I show here, they're not bad. So if you take so check the top left, so example. So this is a house. So this is a house, right? Basically, but then the alt text is the just of this house. So surely you don't want to, maybe not good for you to kind of do this kind of matching, right? So you would probably more want to say a real description of the image. And then we want to do recaptioning. So then we can generate a high quality captions via an external model. And then in the VClip paper, so which is also by Apple, so we collect such data and then do clip training. And so I think so we just show so the data is very useful for clip training, and surely it can be also for multimodal LLM training as well. So due to the use of a model, an external model, but not like GPT-4, so we can actually rapidly scaling up the recipe to billions of images for the recaption work. Well, indeed, we see some similar work in the community as well. DALL-E3 is the most notable example, right? In order to train a DALL-E3 model, you first probably need to generate a detailed image caption and then revert it back for your text to image model pre-training. So in the in CVPR, right, just this year, right, we can see the capsule fusion, also the shared GPT-4 data, and also the lava recap data Chun just mentioned, and also one archive paper just shown maybe 2 days ago, the recap data count 1B by using the Llama 3 8B model to do the recaptioning job. Then is the interleaved image text data. So I think the interleaved image text data is very unique due to this is actually trying to expand the LM style data to images. So because most of the data they are just in the form of your web page, right? When you see one web page, the data is not just text only. So when you construct your text only data, usually you will just remove all these images. But then if you add it back, then it's your interleaved image text data. So it can be very general and across many different styles, but then general the concept is interleaved, so image text by nature. So here this is the data that we have so built, but then so the amount is not important, but then the quality is important. At least we need to do careful image filtering and the deduplication so that you can have good data. So there are also similar data in the community for sure, right? In the early days, Flamingo and also Cosmos One, they have the data, but not open source. For the open source one, there's NMC4 and Oblisis, yeah, forgive me if I pronounce it wrong. And also the Omni corpus. So there are different strategies that we can do for preparing this data. For example, in MMC4, they employ a retrieval strategy. That is, you are going to insert your image into the text sequence based on your clip score. And then in some other data sets, they will just maintain the natural layout of your source web page. And then I think there is also a great opportunity for you to do model-based filtering. So there are many lessons that we learn from this exercise. One, so I think so maybe it's common sense, but then so it's good to also just point it out. It's if you care about few shot and few shot in context learning, so interleaved data will be just very important. So interleaved data is very essential for few shot and text only performance. For few shot is some natural, right? So as you can see from the number I show here, and then it's also essential for text only data, because if you remove the image, then it becomes text only data. So while captioning data will lift your zero shot performance, because by nature your image your captioning data is an image text pair, right? So if you use this data for pre-training, surely you will get decent zero shot performance. As I just mentioned, text-only data helps with few shot and the text-only performance as well. So if you see, so for this one, if you see the blue and the orange number, so the blue is just using the captioning data, and the orange is captioning data plus text-only data. And then you will see, without seeing interleaved data, the model can also have decent few shot performance. So this means your in-context learning capability, in some way, it is not just to your interleaved image text data, but more to the nature of your text-only data. So due to kind of you learn how to, well, this is also reasonable, right? Because we have shown language model training in this way can already show strong in-context learning so capability, but then so in the pure so text side. Yeah, so the text-only data, no surprise, also improve text-only performance. Then the problem is how we can mix them together, right? So I think intuitively, the more text-only data you have, the better your text-only performance. But then if you increase your text-only data too much, maybe it will hurt your multimodal performance. And in this way, so in this work, we just take 10% of the text-only data because your because your LLM is already so pre-trained. But then surely this may not be the so optimal so recipe. So the last lesson that we learned is synthetic data helps with few shot learning. So if you see this number, the blue with the orange. So if you have a high quality image captioning, so this will help your few shot. So then comes to our final model and our final training recipe. So I think for this model, family, we didn't grow image encoder size to an even larger one because we tried some initial experiments and it seems, at least in our current setting, seems it's not ideal. But then we will just stick to the huge model size. And then we have a dense model size from 3B to 7B and 30B. And then in order, so since you are doing pre-training and it can be relatively heavy, so here we also trying to fit a curve to find the optimal so learning rate for your so for your multimodal so pre-training. So basically we are trying to find to fit a curve and then so first to pre-train several relatively small sized model such as 100 million or 200 million and then trying to find the optimal so learning rate for each model size and then so then for the 30B model, so pre-training, we will just use the predicted learning rate, so for the model training. There are different ways to do the scaling, right? One is you can scaling your model size through so the dense model. And then another way you can do is through MOE. And the good thing about MOE is you can scale the number of parameters while keeping the activated number of parameters constant. Due to the total parameter is you have more and more parameter, but then in each forward pass, you only have a constant number of so parameters being activated. So the way that we do MOE, right, just follow the literature, you can add multiple FFM layer, then your original FFM layer will become a set of FFM layer, and then you will do routing so that so you can train your MOE model. So here we are using the sparse upcycling. That is, you are not going to train your model from scratch, but then you are going to initialize your MOE model through your dense model. So so by the end, we studied two model sites. One is the 3B MOE with so 64 experts, and then we are inserting this the sparse layer in every 2 layers. Then this means in total there are 64 billion parameters in total. And another one is the 7B MOE. Then the interesting thing is although it's a 7B, right? But then actually the total number of parameters is so in this study is less due to we are doing sparse layer in every 4 layers. So but then how are you going to train this MOE model? So basically you start with your dense LLM, right? And then how we can go to the multimodal MOE. Well, there are only two choices basically. One is you first do upcycling. You make your dense LLM become MOE LLM, and then you do MM pre-training, then make your MOE LLM become MOE, MM1, right? This is the first way that we can do. Another is the opposite, which is also so intuitive. It's you first make your dense LM become a dense MM1, and then you upcycle your dense MM1 become a MOE MM1. So empirically, I think in the paper we show the results of using the upper approach. It's first do upcycling of the LM and then do the multimodal pre-training. The high-level result is so through this exercise we can so comparing with the Flamingo and also the Emu2. So through this exercise we can got SOTA performance, and then intuitively increasing your number of shots will also improve your performance. And then indeed we think the few shot performance is more meaningful than zero shot, because in zero shot essentially there's no real zero shot, right? When you have a good zero shot performance, it only means your pre-training data fits your downstream evaluation better. So here, but then if you evaluate the few shot, this so this may tell you more information, because you are letting the model to adapt to your downstream data. And as I mentioned, so I think the in-context learning is akin to instruction following, as the demonstration can be considered as repeat instructions. Well, I will not talk about the SFT too much, but then the high level is we just follow the Lava setup using the kind of popular data that has also been used in the Lava Next so model to do the SFT. So the one thing that I would I try to so I want to mention is how you can afford higher resolution fine-tuning. So I think due to your pre-training, right, you cannot increase your image resolution larger and larger, right? But then this can be done during a SFT. So the way that we do high resolution fine-tuning are two ways. One is your positional embedding interpretation. Then this will effectively improve your resolution to 672 so image pixel already. Then the next stage is follow the typical pipeline, such as AnyRes or the Sphinx kind of methods to do sub-image decomposition, so that you can afford the image resolution goes beyond the 1000 pixel. And then we find that this exercise will be very helpful for text-rich image understanding. And then also we find it's better to you to unfrozen all the components of your model, because now we are also doing positional embedding interpretation, right? If you fix your image encoder, it's kind of your image encoder is trained with so your image encoder is trained with a lower resolution. If you just frozen your image encoder, maybe your model, your image encoder cannot adapt to the new behavior of the higher resolution. So in our model, we just unfrozen so demo. But then you also need to be careful about your learning rate. So otherwise, you will also destroy the knowledge you have learned in your image encoder. Well, the idea is not ours, right? It's widely accepted in the in the community. One notable example is the Intel LM work. I think they support image resolution as high as more than 4K. So I think we have pretty SOTA performance on 3B back then, but I think now so we are lagging. So that model is lagging behind the surprise revision. And then we also show MOE has greater potential. And through the way that we do pre-training, we indeed find that we can do few shot prompting. So for example, the 8-shot prompting on the Mass Vista data sets can help us to jump the results from less than 40 goes to almost 45. So well, it's I almost took 45 minutes on this part, but then so I also want to spend some time to discuss some other model architecture design that is possible beyond just the Lava style or the Flamingo style. So I think this also relates to the unification of image understanding and the generation, and even also potentially grounding, right? So I just divided the model into 4 categories. Well, I think different people may have different flavor. It's just the way I do it. So I think it's let's first see the top left. Yeah. So this is what we have covered so far. You have a continuous image feature in, right? And then you have your text token out. And then you also do not enforce image loss during your model training. One interesting example is Fuyu. So I think Fuyu is different from Flamingo or other model. So I think in Fuyu, there's even no image encoder, right? So this is quite a surprising design. So although the similar idea has also been used in the YLT paper before, but I think Fuyu is indeed interesting in the sense there is no such clip, so image encoder. So the prompts will be a vanilla decode-only architecture, right? With no specialized image encoder. It's really unique, right? Just a transformer and then that's it. But then the cons is your model training can be very challenging, right? Because you need to learn the image semantics just from scratch. And then you want to have one transformer and even one LM transformer to do the both image encoder job and also your text understanding job. The second one, I think it's now is not very popular, but I think back then it's kind of also a popular way to do multimodal pre-training. So it's typically it's an encoder decoder architecture. So it's not decode only or not a decode only. It's an encoder decoder architecture. So so I think it's a continuous feature in, and then you have your text and the discrete image tokens out. So you will still have cross entropy loss on both the image and the text token, but then your image has already become token, right? So so you have both so cross entropy loss on image and the text token. So I think one good example is the unified I/O, right? So I think the prompts it's it's also a unified model, right? And then everything is discrete, so which is good. But then the cons is, I think, for example, in this model, due to its encoder-decoder model, right? But then the current popular LM typically are just the decoder only. So how to leverage the LM is relatively less clear. And then the VQ GAN tokenizer can be the bottleneck, or at least the diffusion model is the mainstream. I mean, for image generation or other modality generation. Just some comments, but then so I think so we should always keep different methods open. So the third way is continuous image feature in and text and a continuous image feature out. So and then the continuous image feature will be further connected into a diffusion model, and then typically there will be one L1 loss on your image feature. And then this can also be extended to other model family like any-to-any so modality. So any modality in and then any modality out. So I think the good thing about this model it's based upon your Flamingo-like model or based upon your MM1-like model, right? So you will maintain your strong image understanding capability. But then the cons is the mixed use of cross entropy loss and L1 loss for training may be not desirable or can be unstable in some way. So here, basically, you are going to not using cross entropy for training, but then you are going to use the L1 loss to regress your output image feature to the diffusion model, so embedding space. So I also want to briefly discuss the last model family, which is discrete image and discrete tokens in and out. And also it's in so unified LM. So basically now you have one LM, everything is discrete, and then you do a model training. So I think the CM3 so series of work by Manta is kind of a typical example. They even have 3 models in their development. So so I think this approach is also very interesting. However, the current score on multimodal understanding benchmark seems not very strong. So I think one reason could be your discrete image token trained by your VQ GAN. So this kind of methods can be less informative. And then this can act in as an information so bottleneck for your image understanding. So imagine you have a discrete image tokens, right? So intuitively, the information contained in this discrete image token can be less informative than your continuous so image feature, unless you really have a lot of image token, right? Or your vocabulary size is really large. So indeed, so I think So in the literature, there's another line of work is the seed work, right? They have the seed and then so seed llama, so by Tencent. So I think it's so the visual tokenizer can be the key, but then making it more semantic can be really helpful. So I think here they trying to train your tokenizer in a different way, rather than just using virtual GAN kind of loss for image reconstruction, but then also add a clip-like loss to train the tokenizer. So I think this line is very interesting, but then indeed for the current literature, is indeed the performance on image understanding is not strong as a lava-like model. And actually in their newest model, which is called the SeedX, they choose back to use continuous feature. So which is kind of so interesting. So so I think these are all different kinds of so model architecture design in the community. So I would just want to say, so we have the design choices go beyond the Lava and go beyond the MM1. So I think in this tutorial, so in this talk, I'm using MM1 to show how we can pre-train a multimodal LLM. But then the similar, so I would expect the similar so lesson could be also be interesting to be conducted for other model architectures. And then we also discuss other types of model architectures such as Fuyu, EMU2, and the seed. And then also I have some simple reflection, but then it's just my personal thoughts. So I think for one, it's in order to further enhance pre-training. So the question is, well, we always have a large of amount of data, right, in terms of pre-training. But then how we can, like SFT, right, how we can obtain higher quality pre-training data while more careful model-based filtering could be so interesting. And also how we can use pre-training data from more diverse data sources, right? So for the current model, I think most of the data used for pre-training is just web image text, which in some way can be limited, right? But then if you think about the LM community, they also use a lot of so textbook data and etc. So, so I think in the multimodal pre-training, there could be similar opportunities here. It's how we can get such kind of multimodal pre-training data in this way for pre-training. The next is how we can pre-train the next generation so visual encoder for multimodal LM. So I think clip is the most widely choice, right? But then this may not be true, right? So, so for example, how you can have an image encoder that can both have good so global image understanding capability plus fine-grained image understanding capability, right? How you can so because I think nowadays many of the topic have been switching to multimodal LM, right? But then vision foundation model, I mean, here when I say vision, it's really vision, right? It's you are talking about pre-train your image encoder. So how you cannot imagine Dino V2 and the clip is the end of the story, right? There must be next generation of your image encoder that is under the hood, right? So then that is also a very good question. It's how you can train the next generation vision encoder for your multimodal LM. Also, how you can design better MOE architecture. So I think the way that we use MOE in the MMM paper is pretty straightforward. It's just an MOE. You extend your language only MOE into a multimodal MOE, right? But then things can be different because now you become multimodality, right? So maybe you can design some specific experts for your vision side, or some specific experts for each of your modality. That could be open out of other model choices. Also, we should be open to different model architecture. How we can train performant for you and the seed-like methods to also allow this model to be on the top tier of the model family. So well, you can also imagine how can you use multimodal data to enhance LM instead, right? Well, this is largely unsolved problem because indeed I think there are papers to show using so vision language pre-training or this kind of idea can show improve on LM. But in the mainstream community, I think mostly is still, we just use text-only data for text-only pre-training. So we don't have the answer. Lastly, this is even unknown, right? Unless you join OpenAI, right? It's how you can pre-train GPT-4 like model. I think it's so largely so unknown to us and also keen to our interest. So with that being said, I'm going to conclude my talk here. And then, so I think the slides will also be shared later.